like to welcome everybody to Koç University Science Society's presentation, The Physics of Interstellar. Is it science? Is it fiction? This seminar will be given by Koç University Physics Department, Professor Tekin Dereli. We are honored and very thankful to him for his work and effort to give us this wonderful presentation. Also, I would like to thank people from Koç University Communications Office and Curious Popular Science website, especially Elif Yılmaz and designer of our poster, Cem Çetin. Now let me briefly introduce our teacher, Tekin Dereli. Tekin Dereli received his BS degree in 1971 and PhD degree in 1976 from Middle East Technical University. He had several visiting research appointments over the years at universities in USA, UK, Germany, Austria, and Italy. His main research interests focus on quantum gauge field theories, gravitation and cosmology, on which he published over 120 papers. He is a member of our university since 2001. He received Sedat Simavi Foundation Science Prize in 1989, Professor Mustafa Parlar Foundation Science Prize in 1993, and TÜBİTAK Science Prize in 1996 before coming to Koç University. Now I leave the floor to Tekin Dereli, and I hope you will enjoy this presentation.
Well, thank you very much for the introduction and organizing this nice meeting. I think for several years, I think the Science Society was not active, and I hope that this will be a good beginning for our Science Society activities again. Actually, I should like to start with asking how many of you have seen the movie, in fact? Almost all. So, in fact, I should remind you that the movie Interstellar is shot with a couple of guidelines set by the physicists. It has a scientific consultant who is one of the famous general relativists at Caltech. He's an emeritus professor, Kip Thorne, and he actually retired in 2009, and then he was involved in making these movies and really popularizing science, and he was a consultant of this film, and he set these guidelines before shooting this film. First, nothing should violate the established laws of physics, and second, if there is going to be speculations, which there are, they should come from the sciences, not from the science fiction writers. These are the two guidelines. And when you watch the movie, you realize that the story is full of symbolisms, and there is also amazing sound and visual effects that keep you at full attention for 3 hours. It's a long film, but you don't realize how the time passes. But since my time for this talk is short, I just want to concentrate on the scientific concepts, physics concepts, on which the story evolves, and discuss briefly how these concepts relate to our current understanding of nature. Well, to summarize in one sentence what the movie is about, well, NASA has organized a team of astronauts, a space mission, to search for a new planet, perhaps outside our own galaxy, which will support human life to inhabit when we run the resources of our own Earth out, so we can move on to this new planet and we can live happily there ever after. So they are looking for a new planet which is habitable for the human race. Now, travel in space is something that we managed to do. I mean, recently remember that there was a European Space Agency mission to one of the comets near the planet Jupiter. It landed on there. Its battery ran out, unfortunately, but it took 10 years for that space vehicle to reach the planet Jupiter, which is a neighboring planet, and comparing the scales involved in astrophysics, it is just near. There is one big limitation for space travel. And this is the fact that nothing can travel, nothing can move faster than the speed of light in empty space, which we know it is 300,000 kilometers per second. According to our daily experiences, it's a huge, very large speed, but looking at the distances involved in space and in astrophysics, it is a finite speed. In fact, if you think about light emitted from the surface of the sun, it takes about 10 minutes to reach the surface of the Earth. And as I told you in the previous example, a space vehicle which travels at a speed much less than the speed of light, it took 10 years for it to reach Jupiter. And we are talking about space travel to planets outside our own galaxy, which would take centuries by our own time intervals. And also there is another limitation in travel in time. I am not going to talk about these concepts of space and time and a concept of space-time, but time travel also is something quite restricted, which is not usually what we do, because we know that time always flows from the past into the future. We cannot change the direction of time flow. There is an arrow of time, which is implied by the causality. There is a natural chronological ordering of events. Always the past events is always come before the future events. Cause and effect relations tell us about the direction of time flow. So in the movie, at the end, you will see that there is also a time travel involved. These are very strong restrictions, physical restrictions of travel in space and travel in time. Now, the concept of space-time is the subject matter of special relativity introduced by Einstein in 1905, which implies also some unexpected results, effects such as the time dilation and length contraction. I'm just going to indicate twin paradox here, but I'm not going to talk about that one. But I will discuss a few things about time dilation, which is also an important point in the movie. Now, special relativity was discovered by Einstein in 1905 as a young PhD student. However, the time was right for that discovery. If it was not Einstein, it would have been Lorentz, or it would have been Poincare, or it would have been some other physicist or mathematician who would have discovered it in a few years' time. But the matter with his later theory, general relativity, which is discovered in 1915, 10 years later, is different. In fact, general relativity, the name of that theory is somewhat misleading. It's a dynamical theory of four-dimensional space-time. It's a Riemannian space-time. In fact, it's a relativistic theory of gravitation. Now, in order to appreciate the general relativity theory, I think I would like to give the example of your freshman physics that most of you have taken this year. Well, you learn about Newton's equations of motion that tells you how a particle moves in space. Then, in order to derive the elliptical orbit of the planets, you have to put on the right-hand side the universal law of gravitation, the inverse square force law. Now, when you combine these two, you can obtain the orbit equation, and you can solve it and get the ellipses as the orbits of the planets. Now, going from special relativity to general relativity is very much like this analogy. In special relativity theory, Einstein's paper on this subject concerns the electrodynamics of charges in motion. So it tells you about how electrically charged particles move in space. Now, if you want to find the corresponding theory of gravitation, relativistic theory of gravitation, that will be the analog of Newton's universal law of gravity. So if Einstein had discovered it in 10 years, which was a long time, he worked on it very hard, he had to learn Riemannian geometry, he had to also develop his own concepts of space and time and a curved space-time. It would have been discovered probably in 1960s, after 50 years. Probably nobody else would have discovered it at the time. So Einstein was far ahead of his time when he was stating general relativity theory. And the long-range universal gravitational attraction between massive bodies in his theory is due to the curvature of space-time. And Einstein's field equations that are postulated are second-order partial differential equations which couple the geometry of space-time to distribution of matter. If you give a distribution of matter, it will produce a curvature of space-time which will induce gravitational attraction of the bodies. If you put a very heavy body at the center, it will curve the space-time around it. And if you put a test mass somewhere around it, it will be attracted. It will fall towards the heavy body, and you interpret this as the action of a gravitational force. Now, the predictions of general relativity that we are still working on are important. The first one is black holes, that's what I'm going to talk about. The second one, gravitational waves. They are like electromagnetic waves. Light is a form of electromagnetic wave with a certain wavelength in a certain range. Gravitational waves admitted by Einstein field equations are something similar. They are ripples in space-time curvature that propagate in empty space at the speed of light. Now this is also used in the story of the movie at the end, but I will come back to that, and I'm not going to dwell any more on that concept here. And a third prediction of general relativity is important, but I'm not going to talk about that. It is the concept of a dynamical expanding universe is motivated by general relativity. Because without this general relativity theory, where space-time concepts are combined into a curved space-time concept, we wouldn't have even imagined a dynamical universe, picture of a universe, expanding universe. This idea was confirmed during the 1930s by Hubble, Edwin Hubble. And then it led to the Big Bang theory of our cosmological ideas. And it also gives us a prediction of the age of the universe, starting from time t equals 0. Now these predictions are important, and we believe that Einstein's theory of gravity is correct because we tested. There are very few experimental observational tests of general relativity, which are all within our solar system. For instance, the trajectory of Mercury, which is the innermost planet in our solar system, the orbit is an ellipse, which is very flat, almost. It's the flattest orbit in our solar system. Well, the ellipse do not close in one revolution. It precesses. We call it the advance of the precession of the perihelion of Mercury. Well, it completes one revolution in 260,000 years. The ellipse revolves around it. It comes back to the original ellipse in 260,000 years. But this is something that can be determined at the end of the 19th century. And the paradox is that classical theory of gravity, as proposed by Isaac Newton, was unable to account for about 42 seconds of an arc per century. And general relativity can give the exact amount. And also the bending of light rays as they pass through near the sun. In Newton's theory, the light doesn't interact with gravity. It doesn't feel the gravitational force. But in Einstein's general relativity theory, the light bends as it moves close to a heavy object like the sun. This is also predicted, confirmed. So we have confidence in Einstein's theory, and since we have confidence in Einstein's gravitational theory, we also think very seriously about the possibility of having a black hole, about the possibility of having a gravitational wave propagating in empty space, and also we are very confident about the expanding universe picture that is based on a Big Bang idea. Well, okay. are they real? Do we observe black holes? Do we observe gravitational waves? Maybe I should answer the second question first. Up to this point, up to today, there is no direct evidence that the gravitational waves exist. There are very ambitious projects to measure gravitational waves with no results up to this point. With the black holes, we are more lucky. There are some candidates of black holes that are observed in the sky. Now, the observable black holes are formed by the gravitational collapse of heavy stars at the end of their life cycle. Now, what keeps a star in equilibrium and keep on shining is the thermonuclear fusion reactions that take place at its core. Hydrogen is fused into helium with a release of energy. This is one cycle. When the hydrogen fuel is exhausted, helium atoms can merge into lithium. That's the second cycle that still generates energy. This energy generation by fusion mechanism goes up to the iron, and after which it burns out its nuclear fuel. And then I'm not going to tell about the life cycle of a star, but heavy stars, something like a few solar mass stars, at the end of the life cycle have no support for their equilibrium, and they collapse under their own gravitational attraction. And they can get very small, and the density can become very large, and such objects are candidates for black holes. Now, where do we see such objects? The candidates for black holes in the sky came from double stars. A double star, two objects about the same mass, can revolve about each other. And since there is angular momentum, the angular momentum is perpendicular to the ecliptic plane. Now, if you see a star that is rotating in an ecliptic plane, and if you don't see the partner star, then that partner star is very probably a black hole, which keeps the star running around. It's also running around, but we don't see it because there is nothing that comes out of the black hole. Now, how do we see a black hole? That's the question. I'm going to answer that. And what is inside a black hole? These are two important questions. Now, a black hole is characterized by an essential curvature singularity that lives in the center. This is where the curvature becomes infinitely large. It means that the gravitational attraction becomes infinitely large as you approach the center origin. However, we don't see this singularity from outside because it is covered by what's called an event horizon. Now, an event horizon is a two-sphere that covers a point.
Sorry, what do you understand saying infinitely large?
Infinitely large.
As a physicist.
As a physicist?
Yes.
Okay. I have to maybe go a little bit technical here. The space-time is Riemannian. It's an Einsteinian space-time. If you think about the exterior gravitational field of a static spherical mass distribution, the exterior gravitational field around this static object is described with what's called the Schwarzschild metric. And then you can calculate the quadratic curvature invariant of the Schwarzschild metric, which is asymptotically flat. So R goes to infinity, the metric goes flat. But there is nothing else I can do at this point. But you can think about, for instance, the universal law of gravity predicted by Newton, 1 over r squared law. It's asymptotically flat. As r goes to infinity, the force dies down to 0.
Very, very big, but infinitely large means very, very thick.
Well, actually, the quadratic curvature invariant goes as 1 over r to the 6. So when r goes to 0, it goes up. It means essential curvature singularity. It becomes very big. Well, what's important is the event horizon. Any object near a black hole is pointed across the event horizon, and nothing can come out of it because the gravitational pull is so strong. So think about the other way around. I think I want to describe the event horizon in a different way. Suppose that a star had become an event horizon. What it means is that the surface of the star is within its event horizon. It's so small. For instance, for our Earth, we can estimate the mass of the Earth, and its event horizon is a few centimeters. And if you think about the Sun, it's a huge object, very heavy. Its event horizon is a few kilometers at the core, right? So I'm talking about densities such that the whole mass of the Earth is concentrated in a sphere of 1 centimeter in radius. Right? Okay. That's a black hole. Now, the gravitational pull of such an object is so strong that it won't leave the light emitted from its surface. It will slow it down. It will slow down. It cannot escape. It hovers over the sphere. And that's what's called the event horizon. That's the definition of Roger Penrose, in fact. So event horizon means that the light emitted from the surface of the black hole hovers on a sphere. It will just waits there. It cannot go out. It cannot fall back. It just moves on the sphere. That's the event horizon. But the event horizon is such a distance. If there is anything outside, it will pull to the black hole. When it goes into the event horizon, it cannot come back. Nothing comes out of the black hole. That is our expectation. So the question arises, how do we see a black hole? And what is inside a black hole? If nothing comes out of a black hole, you won't know what's the inner structure of a black hole. You all know is event horizon and the exterior gravitational field outside the event horizon. Now, how can a black hole be observed from outside? Can be answered by my previous example of a double star. Now, you see that when a double star is formed with one partner being a black hole, its gravitational field is so strong, it can pull mass out of the visible partner. And that matter that is pulled out of the visible star will spiral into the black hole in the ecliptic plane. So as it spirals in, it means that the charges accelerate, and accelerating charges radiate electromagnetic waves. So you see the black hole very bright. But it is not because of the gravitational field that we observe, but it is because the electromagnetic waves radiated by charged particles spiraling into the black hole. Okay? So this is one way of seeing the black hole in double stars with an invisible partner. And there are candidate black holes in our own galaxy and other galaxies. A second place where you can see a black hole is at the galactic center. Our Milky Way galaxy is flat like a disk with bumps in the middle. It is huge with arms and it is rotating. And then at the galactic center, very galactic center, we expect to have a gigantic black hole. Now, you cannot see it. It's a single black hole, but it is so heavy, 10 times, 18 times heavier than a double star. It is an extremely huge black hole. It attracts stars around it, and the density of stars at the galactic center is more than the average density of stars in the galaxy. So there is an accumulation of mass around the black hole, and if you observe that accumulation of mass around the black hole, you can guess that there is something that's pulling the mass to that point. So very probably our own galactic center has a gigantic black hole, but there are other candidates, double stars with an invisible partner. They are also black holes. Now, in fact, in the movie, the astronauts go into the black hole, and they survive. Well, that's the fiction part, because if you again come to the mathematics of gravitational fields, the gravitational fields is not like electromagnetic fields. They are much more complicated than that. They produce tidal forces. Well, it means that, suppose that you are sending an astronaut towards the event horizon, like Superman, in a horizontal way, right? Now the gravitational field is so strong that the gravitational field felt at the head is greater than the gravitational field at the feet, right? So that much difference is quite high for a black hole, in the neighborhood of a black hole. So when an astronaut approaches a black hole like that, like Superman diving in, he will get stretched. These are tidal forces, but not enough. It will be also pulled at the sides, right? Stretched and pulled to the side. So an astronaut diving into a black hole will become like a pack of spaghetti. That's what we expect, studying the forces acting on an object falling into a black hole. Well, this is also called spaghettification. An object falling into a black hole must have shown this effect of spaghettification. And in the film, of course, we don't see it. But gravitational tidal forces are important because the gravity is so strong near the event horizon. And also I have to talk about communication with outside observers. We are sending a mission to go inside a black hole, astronauts. And then, of course, you have to sit in Earth and waiting for a news, right? What's inside a black hole? How does the event horizon look like, right? How do you communicate? In the movie, of course, they exchange video messages, computer screens, etc. Well, let us keep the argument simple. You take a watch, right? It just tick, tick, tick, tick, tick, it keeps time. And then you give a similar watch to the astronaut that starts to travel, which the clocks synchronize with each other. They are ticking at the same rate. Now, as the astronaut starts to move at a constant speed at first, let me say, there is time dilation. If you are observer at rest on the Earth, and if the astronaut is moving away from you at a constant speed, then the time intervals between two ticks is slowed down. That's a fact. Your watch goes tick, tick, tick, tick, tick, and the watch, the signals that he's sending back will be slower. What does it mean? I am aging a lot faster than the astronaut, right? Now, a gravitational field also changes the rate of time. So, the signal that tells us that the astronaut is passing through the event horizon is the following fact. As the astronaut approaches the black hole, the gravitational field starts to intensify. Now that makes the time interval of his signals coming back longer and longer. So you wait, well, you started at 1 second time intervals, ticking at 1 second time intervals. As it travels in space, his time interval is longer, but at a steady rate. But as the astronaut approaches the black hole, the time interval between two ticks starts to increase. Increase. You start to wait ages to get a second tick. And at the end, at the moment when the astronaut passes across the event horizon, you don't get any more signals. So you wait for eternity. It means that the astronaut has gone into the black hole. His own watch, according to him, to the astronaut, is tick, tick, tick, tick, tick, it doesn't matter. But the observer at rest on the Earth sees that it is getting slower, infinitely slower, and then it stops. Right? That is when the astronaut goes into the black hole. No more communication, nothing can come out of it, and it is lost. Right? So that is actually how we know that the astronaut has fallen into the black hole, staying at the Earth. Now, in fact, I should maybe say a few words about the I have to say a few words about this time dilation effect. This is the time dilation effect that I have explained. The fact that in special relativity theory this is reciprocal. That I am at rest and my twin traveling at a constant speed, the astronaut, his watch is ticking slowly compared to my watch. So I am living very fast. His lifetime is getting longer and longer compared to myself. But what is curious about relativity is that this is a reciprocal effect. According to the astronaut, in his own frame of reference, it is us that are moving backwards on the Earth. So he thinks that his rate of his watch is tick, tick, tick, tick, tick. It's the same rate. And then he looks at us at the back on the Earth. We are slowing down. And that's the essentially twin paradox. I'm staying on the Earth and think that he stays younger. Astronaut travels to the star, taking his own time with his own watch, and he thinks that I have aged, not him. Now what can be true? This is a paradox, twin paradox, but it's not a paradox. Why? In the solution of the twin paradox, you take the twin on the Earth, okay, he's staying on the Earth. The other twin, he has to travel at a constant speed. So outgoing twin, that's fine. He's traveling at a constant speed. But in order to compare their ages, he has to come back to the Earth. Right? So he comes back to the Earth at a constant speed again. Again, the same effect applies. But what about the turning point? So the twin who is traveling in his spacecraft stops, turns around, and comes back. And he thinks that the Earth has stopped and is coming back. But it's not the case, right? If he takes an electric charge with him, and if I have an electric charge with me, on the Earth, my electric charge do not radiate. But if you look at the electric charge carried by the astronaut twin, at the instant he stops and turns back, it will radiate. It will just give just a single light. So you would know who's traveling and who's not traveling. So it's not a paradox at all, because there is at least one instant of time the system accelerates, and the law of special relativity do not apply to the twin that's traveling. So you would know who's traveling and who's not traveling. So twin paradox is not a paradox at all. Okay. So this is, in fact, this is the science. Maybe I should also comment about this one. This I got from the internet, and you see this picture at one point during the film. But this is a simulation done by Kip Thorne. This is the accretion disk that I'm talking about. There is a black hole at the center. And what is this round thing here? Now that's the effect of gravitational lensing. I told you that the light passing near a heavy object is bent from its straight line path, right? So this, in fact, is a halo. The stars behind it are seen by a gravitational lensing as a circle around it, a bright lensing. So gravitational lensing is, in fact, is the image of stars behind the black hole. Black hole is at the center. Now, in fact, this is an amazing picture. I haven't seen the original simulation result because Thorne is telling that he's going to publish papers out of it. He's lucky because, in fact, in order to make this simulation, it is done by the visual effect firm Double Negative. A team of 30 data scientists worked with Kip Thorne to integrate Einstein's equations. They generated, according to Kip Thorne, 800 terabytes of data to generate this picture. It's a very nice picture. It's a simulation. And this is how actual black hole would look like. Now the astronaut traveling to a black hole towards a black hole would have seen this picture here. So this is science, but maybe I should open a parenthesis here. A simulation result. We believe in Einstein equations. We think that it is true. And we can integrate it numerically to generate such pictures. Is this reality or not? Well, I think there is a lot to discuss at this point.
Integrating numerically, meaning finding approximate solutions.
Well, I mean, this is a very good approximation.
Yes, but not the exact solution.
Well, yes, yeah. Yeah, but,
Yeah.
but
Anyway, it's good.
no, it's true. So this is a black hole. How a black hole would look, if there is any. Well, in fact, a black hole just on its own is not sufficient to explain space travel that takes place in Interstellar. You need something called a wormhole. It's translated into Turkish as solucan deliği, that I don't like. I call it a tüp geçit. I call it a tüp geçit. Why? Because what a wormhole is doing is that you have to do a topological surgery on the fabric of spacetimes. I think the topologists here will understand what I'm talking about. A spacetime is a four-dimensional manifold. You can puncture them. Just take one point out, that's a black hole. You take another point out, that's the second black hole or white hole, and then you put a handle. Right? So you change the topology of space-time. You increase the genus by one. So that's a topological surgery. That's a wormhole, handle.
So that's what they explain in this white paper, right? So they folded the paper, put a hole, and that's what you're telling me.
Tüp geçit.
Yes.
Okay, you go out from this point, you go through the tüp geçit and come to the other point.
So that's what they explain in the
Yeah.
paper.
Right. So, if there is a wormhole in nature, I think that you can use it for time travel or even space travel.
They said it's a shortcut.
It's a shortcut in space-time. Actually, I had given a talk several years ago here on time travel, and I had given the same example as a time machine. Because it's a shortcut. Instead of going the long way, you can take a shortcut, so you go to the past of the arrival point.
But then you don't go through the black hole, actually.
No. What's a wormhole is something that's interesting. The one end of the wormhole is a black hole. Everything goes in. The other end is a white hole. Everything goes out. One's a source, the other is a sink. Black hole is a sink, white hole is a source. Now, is there any white hole in nature? What? If you believe in Einstein equations do not care about the direction of time flow. Right? They are time reversible. You can go either from past into the future, you get the same equations, same solutions, or you can go from future to the past, and you get the same solutions. Well, what distinguishes past from the future is the boundary conditions that you impose, causality. But since the Einstein equations are time reversible, if you have solutions which are interpreted as black holes, you will have also solutions which will be interpreted as white holes. Black holes will attract anything that is in its neighborhood. Nothing comes out of it. White holes are solutions of the Einstein equations which do exactly the opposite. It throws out anything that's inside, and it doesn't get anything inside of it. It's a white hole. It's a source. Black hole is a sink. So a wormhole, one end is a black hole, the other end is a white hole, and you can travel only in one direction. You cannot go in the opposite direction, because going in the opposite direction means that you are going to dive into a white hole, which is impossible, and then you have to traverse the black hole in the other direction. It means that you are traveling against the arrow of time.
I mean, if you can go from a black hole to a white hole, then that means you can leave the black hole.
Yeah. Well, I mean,
You
it's a
said
trough.
nothing is black hole.
It's a trough. Yeah, that's one problem. It's just you are putting a trough. I mean, you have a funnel here, which is connected to the other one.
So there's a way to get out of the black hole.
If there is a wormhole.
Huh?
If there is a wormhole, yes. you enter a black hole at one point, at one location, then you go to some other location through the light hole. So this is, in fact, the way you have space travel. That's the way they traveled, I mean, in the movie, from this galaxy to a location in another galaxy, for instance. Of course, there are serious problems here. First of all, can you keep the wormhole wide enough so that a spaceship passes through it? It's a big problem. In fact, in order to open the throat of this wormhole, you have to supply a negative pressure, because gravitational attraction pulls everything inwards. In order to keep it open, you have to supply a pressure which pushes it outwards. But ordinary method doesn't do that. So you have to have, for instance, a quantum matter. But quantum matter means that you have to have very thin wormholes. And now we are talking about a spaceship that passes through a wormhole. Well, okay, that's it.
So what you say is that what you say is the conclusion of the assumption is time is reversible, right?
I'm not saying time is reversible.
But you said the Einstein equations do not say about the time direction.
Yeah, but I think it's the same thing with the Newton's equations, for instance. Newton's equations is also time reversible.
But yes, you are right, but when we are solving physics problems, we have two mathematical conclusions and we say this is a physical, this is not physical, since we are believing that time is going in that in one direction. So, but
Yeah, it's the same thing here. You have to impose causality as a boundary condition.
after imposing causality, we are getting one cause again.
Yeah. Here the topology of space-time is different. We are modifying the topology of space-time. So this is, in fact, wormhole solutions exist of Einstein equation. It doesn't mean that this time.
There are imaginary numbers, for example, which are equations, but we know that
But the wormhole solutions, wormhole solutions exist. But the topology is not the topology of the black hole. Okay. Actually, I don't know how natural wormholes will be generated. It's a solution of Einstein equation, but I don't know if they exist or not, because I can see they can be and also, I don't know if we can produce wormholes, because we have to do topological surgery on the fabric of space-time. I cannot even imagine how technologically this could be possible. How do you puncture space-time? Right? I don't know. I mean, there is no technology about it. I cannot even imagine if such a thing is possible or not. So you cannot generate artificial wormholes. You don't know how to do it. Now you have to rely on the existence of natural wormholes. But also now this is a weak point on the story of the movie, because now they have this new planet somewhere in an outer galaxy, and they go into a black hole here, they pass through the wormhole and they go to the planet. Now how would they know that the wormhole will end on that other planet? There is no way of knowing, because we don't know anything about the interior of a black hole. When you dive into a black hole, you don't know whether it's a wormhole or it's just a black hole. You don't have any idea. Now you dive into a black hole, suppose. Now, do you come out somewhere? Where? God knows where. Yeah. Yeah. So that's a weak point, in fact, because you don't know where you are going to end up. And another serious problem is you cannot return back through the same hole. So you must have a second tube agent coming back the same way. Otherwise, you cannot come back, because it means that you are traveling back to the same time. It's not possible. Okay, so wormholes. Well, this is the fiction, right? That's the planet. The water. That's where they end up. Actually, it's somewhere in New Zealand. There's no Iceland. Somewhere in Iceland. They have shock waves, tsunami. They had to escape this tsunami. Escape from this gravity.
And such a big tidal wave, which is left like this.
Well, this is not, in fact, I think the reason why they are walking over the surface is probably it has to do with the magnitude of gravitation, acceleration. It's not the density. I suppose that it is water still. The density of water is known. So probably it has to do with the gravitational acceleration on that planet, that they are walking on the water.
So what would be well, we could really for the
Well, of course, I don't know. That's good.
yeah, this is what I'm thinking about.
Yeah. Well, I told you something more serious than that. If you want to approach a black hole, you will be torn apart immediately. You cannot enter through the black event horizon in one piece.
Yeah, okay. Unless your single atom will contain all your information,
Not even an atom
even
can
the
survive.
subatomic particles will contain your all information. This is possible.
But in fact, there are theorems concerning black holes. A black hole is characterized by its mass, its spin, and its net electric charge alone. Anything else that you put in is lost. Any information is lost. Right? You can throw in astronauts, you can throw in DNAs, you can throw in atoms, you can throw in anything. And all the characteristics are lost. Anything that matters is the total mass, its rotation, and its electric charge, if there is any. And nothing else matters for a black hole.
Can you think about the black hole as a some corridor to other universes?
Well, that's the wormhole.
Sorry?
That's the wormhole.
I see.
That's the corridor to get it to a different galaxy. What do you mean by a different world? It's a different world. In fact, that's one part of the symbolism. In fact, a different world is the world. The mission is called Mission Lazarus. Do you have any idea? This is beyond our culture, in fact. It's a Christian terminology, Lazarus. The parable of Dives and Lazarus. He's the patron saint of lepers. Right? So, in fact, this mission, NASA mission, is called Mission Lazarus because they are getting news from afterlife. Right? And I told you about the black hole and the communication with an astronaut going into a black hole. So it is getting news from afterlife. So that's why in the film the mission is called Lazarus.
And Lazarus is also one of the apostles that Jesus Christ revived, if I'm not mistaken.
Yeah. So you know. So many people, I believe that many people who watched the movie in Turkey didn't know anything about Lazarus. Right? Okay. So there are lots of symbolisms like that.
Very
Okay. Well, suppose somehow the astronauts fall into a black hole passing across its event horizon. What would happen as they approach the essential singularity in one piece? Well, we believe that quantum gravity should take over at that point. You have talked about this, what happens at the singularity, right? The gravitational force becomes so large, gravitational interactions become so large, the distances become so small that quantum effects cannot be neglected. So this happens technically when the Compton wavelength of a particle or a body is of the order of its Schwarzschild radius. At that point, you have to have a theory of gravity and quantum theory valid at the same time. So maybe if you are able to approach the essential singularity at the core of the black hole, at that point, classical laws of physics cease to apply, and you have to find new laws of physics that is called quantum gravity. Fine. If we knew quantum gravity, a consistent theory of quantum gravity, that would have been excellent. But we don't have an excellent, we don't have a consistent theory of quantum gravity. I have worked all my life for such a theory, and I wish somebody behind my library will hand me the equations. This is what happened in the movie. Yeah, a binary code. But that's also, we are coming to that. Okay. So, the closest we can get to quantum gravity today is through the closest we can get to quantum gravity today is superstring models that live in 1 time and 9 space dimensions for consistency. Okay, so we have 6 extra space dimensions which curl up upon themselves. They form a Claudius manifold, 6-dimensional. Okay, that's one assumption. I'm not going to go into any detail about superstring models. So you should think about it as a consistent theory of quantum gravity, which includes all other forces in nature in a non-unified theory. But the other approach, I think that's the approach adopted in the movie, is to think that the space-time loses its continuity. The space is a 3-dimensional continuum. It's a 3-dimensional Euclidean space in non-relativistic physics. And time is regarded as a 1-dimensional continuum. Each point on the real axis, time axis, corresponds to an instant of time. But what I'm saying here is that perhaps when quantum gravity applies, we have to discretize time, and we have to discretize space. Now, there are such approaches to gravity, quantum gravity, in which case this space-time, 4-dimensional space-time, or a higher dimensional space-time is described by a hypercubical lattice, for instance, as it is done in the movie. In the movie, our astronauts fall heroically into a black hole. Right? One of them goes out, the other one goes in order to save the astrophysicist, Amelia Brandt. The astronaut jumps into the black hole, which allows the spaceship, Ranger, to move out, escape the gravitational pull of the black hole. But then our astronauts is deep down into the black hole at the end. Now, it happens that he somehow returns back to the location where he had started from, but at an earlier time in this past. So that's where the time travel occurs. And now you don't understand how it's going to happen. Now, I think that's where our higher dimensional theories come into play. Maybe I'm going to draw this picture here. These higher dimensional theories of gravity are motivated by superstring theories. So maybe we are in a 4-dimensional space-time, but in fact our space-time is 5-dimensional. So this is what's called the bulk, 5D. I wrote this one, let's see. So 5-dimensional bulk, this is our space-time with boundary, like that. So this is a 4-dimensional boundary. And we may have either one other copy or we don't have another copy. We can impose, we are living here. But in fact, we are living on the boundary of a 5-dimensional space-time. And what happens is that in string theories, you can start a string here, and then you can go to a different point. So you can extend into the bulk. So it's just a little bit tricky. These are bulk boundary gravity theories, 5-dimensional. And the effects of the 5th dimension will be felt in our 3-4-dimensional space-time. So what happens probably in the movie is that our astronauts who jumps into the black hole had traveled into the 5th direction, 5th extra dimension, and somehow maneuvered himself into his original location, but at an earlier time. So he traveled in the extra dimension. Was it possible? Well, probably not. But at the end of the movie, he was trapped in what he called a tesseract. It is something like a cage, like in the pictures of Escher, right? He cannot move out, but on the other hand, he sees his old self from the bookshelf. And then he can send a signal, and he can shout. And in fact, his own daughter, many years ago, thinks that there is a ghost, a friendly ghost behind the shelf, because the astronaut who returned back was shouting through the wall, bookshelf. I don't know, this is totally a fiction, of course, but what is more, he managed to send a signal to his old self using a gravitational wave, using a binary code. And he had passed on his knowledge of a quantum gravity theory with a binary code using gravitational waves from a tesseract into a four-dimensional space-time at a time in his past. So his daughter grew up to a scientist, a physicist, and he knew about quantum gravity, so he solved the problem. Well, this is, I think, where fiction is getting far ahead of science, and probably I think it's a good point for me to stop.